Hello students. We'll continue again with unit number 4 and topic number 5, which is Kennedy's theory, design procedure and Lacies theory. Kennedy's theory, it was incorporated in 1895. R.G. Kennedy, an executive engineer of Punjab PWD, carried out extensive investigations on some of the canal reaches in the Upper Bury Doab Canal system. He selected some straight reaches of the canal section which had not posed any silting and scouring problems during the previous 30 years or so. Gerard Kennedy from his observation concluded that the silt supporting power in a channel cross-section is mainly dependent upon the generation of eddies from the bottom width of the channel section rising to the surface. That you can see in the figure. These eddies are generated due to the friction of the flowing water with the channel bottom surface. The vertical component of the eddies tries to move the sediment up while the weight of the sediment tries to bring it down, thus keeping the sediment in suspension. Thus he added, if the velocity is sufficient to generate these eddies so as to keep the sediment just in suspension, silting will be avoided. Then Kennedy stated that a channel is said to be in a state of regime if there is neither silting nor scouring in the channel. In this figure, you can see the generation of eddies from bottom of the channel. Based on that, he defined a critical velocity V0 in channel as the mean velocity, which will keep the channel free from silting or scouring, and related it to the depth of flow by the equation V0 is equal to C suffix 1 dot Y into C suffix 2. Here C suffix 1 and C suffix 2 are constant, which depends on silting discharge. And C suffix 1 value is 0.55 and C suffix 2 is 0.64 in MKS units. So therefore V0 is equal to 0.55 Y into 0.64. Implies V0 is equal to 0.55 my into 0.64. Here m is the critical velocity ratio. Later on, he introduced a factor small m to account for soil type through which the canal passes. This factor, which depends on silt grade, is named as critical velocity ratio CVR, denoted by m. So in place of table 6, it should be table 3, okay? Typing error. So table 3 below shows the value of m for different types of silt. The equation for the critical velocity was then modified as V0 is equal to 0.55 my to the power 0.64, where V0 is equal to critical velocity in channel in meter per second, Y is equal to depth of water in meters, and m is equal to critical velocity ratio CVR. So in this table, silt type and m values are shown. So silt, the first one is silt, its value is 0.7, then light sandy silt 1.0, light sandy silt a little coarser 1.1, sandy loam silt 1.2, and debris of hard soil 1.3. This is the design procedure for Kennedy's theory. The critical velocity V0 is to be determined by the equation V0 is equal to 0.55 my to the power 0.64 by assuming a trial depth. So then determine the area of the channel by dividing the discharge by the critical velocity V0. Next, we have to determine the channel dimensions and finally compute the actual mean velocity, which is capital V, that will prevail in the channel of this cross section by Cutter's formula. So comparing the mean velocity capital V and critical velocity V0, if two velocities V0 and V works out to be the same, then the assumed depth is alright. Otherwise, change it and repeat the procedure till V0 and V becomes equal. So this is the Cutter's formula. So from the above equation, the roughness coefficient is given by capital N, which is called as Cutter's constant. The value of Cutter's constant is also dependent on the roughness of the surface. The slope of the bed is given by small I, and the hydraulic mean depth or hydraulic radius is given by small m. Next, Lacies theory. Lacy carried out an extensive investigation on the design of stable channels. Next, Lacey's theory. Lacey carried out an extensive investigation on the design of stable channels and alluviums. On the basis of this research work, he found many drawbacks in Kennedy's theory and he put forward his new theory. So, Lacey's regime channels. It is stated by Kennedy that a channel is said to be in a state of regime if there is neither silting nor scoring in the channel. But Lacey came out with a statement that even a channel showing no silting and no scoring may actually not be in regime. So he therefore differentiated between three regime conditions: true regime, initial regime, and final regime. So according to him, a channel which is under initial regime is not a channel in regime. True outward lead appears to be in regime as there is no silting or scoring, and hence regime theory is not applicable to such channels. His theory is therefore applicable only to those channels which are either in true regime. A channel shall be in regime if there is neither silting or scoring. For this condition to be satisfied, the sill load entering the channel must be carried through by the channel section or in final regime.
Smart water technology is revolutionizing the operation and management of open canal irrigation water distribution systems around the world, reducing the massive amounts of water lost in transit from storage to farms. Using the world's limited water resources efficiently is becoming increasingly important as the world faces scarcity in many regions. With 70% of the world's fresh water used for irrigation, authorities are looking to reduce water lost in inefficient irrigation infrastructure. In Australia and around the world, canal automation is being implemented to reduce these losses and secure more water for productive uses. In one of the leading projects of its type, the Northern Victoria Irrigation Renewal Project, or NVIRP, is underway in Australia's Murray-Darling Basin. It will secure the future productivity of Victoria's food bowl irrigated agricultural region, while delivering major environmental benefits. The project is automating Goulburn-Murray Irrigation District's 6,000 kilometres of canals, and together with targeted remediation and rationalisation, it will see over 425 gigalitres of water saved each year, a figure similar to the amount of water consumed by the City of Melbourne's 3 million inhabitants. Previously, the district was losing massive amounts of water through leakage and seepage, inaccurate metering and poor control that results from manual operation. It is now being transformed into a modern and efficient supply system that makes the best use of precious water resources. The project's technology is the result of many years of research and development undertaken in conjunction with the University of Melbourne. Called Total Channel Control, it is the world's first fully automated end-to-end canal automation system, enabling efficient operation that is on par with pipe networks, but without the associated costs. It achieves these outstanding results using a combination of precision water control gates, known as flume gates, accurate system-wide flow measurement, wireless radio networks, automated meter outlets, and sophisticated software. The project is transforming the district on a large scale, with some 10,000 flume gates being installed across thousands of kilometres of canals. The entire network is centrally managed using software which automates every aspect of the operation: customer ordering, planning and scheduling, automatically controlling the farmer's outlet, and customer usage and entitlement reporting. Networks of flume gates precisely measure and control the flow of water, constantly adjusting to ensure optimal system operation. Human intervention is only required to address any problems that are identified by comprehensive diagnostics. And through accurate measurement, the system is able to identify high-loss sections of canal for targeted remediation, ensuring limited maintenance resources can be spent to achieve maximum benefit. The technology is achieving outstanding results, with some large-scale operations achieving up to 90% efficiency. The Goulburn Murray Irrigation District is already seeing improvements of around 20% in parts of the district that have been automated. The resulting water savings are being made available for urban uses, returned to river systems, and used for further irrigation. Additionally, NVERP is delivering major service improvements for irrigators. Water can be supplied within 2 hours of ordering and at high and constant flow rates, enabling farmers to achieve major efficiency improvements on farm.
Yeah, on my farm, what it's allowing me to do is to grow a lot more tonnes per megalitre because we're getting bigger flows, consistent flows. The consistency is probably the big thing. You know, it'd go for a couple of hours and then slow up. Now it's exactly the same rate for the exact amount of time, so you can plan it a lot more efficiently. Straight away I can go onto the computer, pretty much water it on demand.
With a modernised supply system, farmers are now able to take efficiency to the next level by automating their on-farm irrigation operation, maximising crop yield and quality while reducing water use. And all this is achieved by harnessing gravity to move water and by using solar-powered gates, meters and radio networks. The NVERP project is a true low-energy, low-carbon solution.